Hello APC Mechanics students in Unit 2 Newton's Laws of Motion, Class 6, Newton's second law, Part 3. Then in today's video we're gonna solve some problems related to what we have explained previously. Then problem 1, so basically this is what we will be expecting in our free response paper. Block 1 and 2 of respective masses m and m, so small m corresponds for block 1, capital M corresponds for block 2 because they set respective. Then this is small m and that would be capital M, are in contact and pushed by force F. The system accelerates by an acceleration A on a horizontal smooth surface. The moment they mention it's smooth, then no friction. Express all algebraic answers in terms of mm, f, phi and physical constants as appropriate. So whenever now we're gonna derive any expression related to any of these parts, we need to make sure that they are expressed in terms of these and physical constants as appropriate. So for example, given by G. Now here, these two blocks will be submitted to an acceleration due to this applied force. Now usually we take the positive direction to be to the right. Now because the system will move to the left, for all of this problem we're gonna consider the left direction to be the positive direction. Then let's start with part A. Now you notice that in part A we're gonna deal with the FBDs. Why FBDs is important? In order to utilize Newton's second law. Then on the dots below that represent block 1, block 2 and the system block 1, 2 separately, draw and label the forces, not components, that act on each body. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So basically they're listing for us the rules that we should follow in order to do the FBD. And in such type of configurations, blocks on a level surface, we may consider different systems. One of them is the block 1 separately, another would be the block 2 separately, and a third configuration would be this system combined, in which it communicates with the force F. For the block 1 we have the pull of gravity down, we have the normal push up, it communicates with the force F making an angle phi with respect to the horizontal. Now notice that the force F is being applied at that point, but we need to follow the rule is that each force must be represented by a distinct arrow starting on and pointing away from the dot. The dot represents the block. For this reason it will be represented from this point, making an angle phi with the horizontal. And we don't forget that block 1 sees block 2 as a support, therefore block 2 will exert a force on block 1 given by the normal push, characteristic similar to the normal push, which is given by F2 on 1. Now for block 2 doesn't communicate with the force F, so let me start by listing the pull of gravity down, and notice that here I have represented this to be Fg2 because it's the pull of gravity of block 2, and this to be pull of gravity of 1, similarly Fn1, and that would be Fn2. And as I've mentioned that block 2 doesn't communicate with this force, so we won't represent it, and there will be a force exerted by 1 on 2 which is pointing toward the left. And as you can see that these two pairs, they form action-reaction pair, and I have represented them in a manner that they are equal, and this is given by Newton's third law. Now for the system as a whole, that would be the pull of gravity down, the normal push up, and the force F making an angle phi with the horizontal. Now in part B we need to derive an expression for the force F21 exerted by block 2 on block 1. Now in order to determine this force, which is the force exerted between the two blocks, we need to use the Newton's second law. But before using Newton's second law, we need to choose which FBD we're gonna utilize. Now F21 appears in both diagrams, FBDs, in this one and in this one. So let me consider in this case this FBD. Why? Because it's being acted by the least amount of forces. Although they're asking me for F21, But since if we are able to calculate F12, we can deduce that F12 is equal to F21 according to Newton's third law, since they form action-reaction pair. But remember that in such type of configurations, before we proceed, we need to determine the acceleration of the system. And this can be done using Newton's second law. And in order to determine the acceleration of the system, we need to consider the FPD initially of the system as a whole. So in this case, the forces acting on the system are the pull of gravity, the normal push, F, and the mass would be replaced by the total mass given by m plus m. Now along the horizontal and taking the left direction to be the positive, pull of gravity 0, normal push is 0. Now what about F? F has both horizontal and vertical component. The horizontal would be F cosine phi, and A has no projections. Now isolating for A would be given by F cosine phi divided by the total mass. But remember that we're not being asked about the mass, we're being asked about the force F12 or F21, and that can be determined first by initiating the acceleration of the system. So now we can apply Newton's second law to block 2. So I repeat and say that my choice went with 2 because it's being acted by the least amount of forces compared to block 1. Now, what are the forces acting on block 2? We have the pull of gravity down, the normal push up, the force F12 left, and this is equal to ma, the mass being replaced by capital M because the capital M is the mass of the block 2. Now along the horizontal, pull of gravity 0, normal push is 0, F12 is completely toward the horizontal to the left, it has no projection and it's positive. And this is ma, so F12 is given by ma, A would be replaced by that, and factoring out the fractional mass, then we now have that F12 is given by this expression, but now we need to deduce F21. F21 can be deduced from F12, stating that F12 equals to F21 according to Newton's third law. Then the force exerted by 2 on 1 that we're being asked about is given by this expression. Now in part C, we need to derive an expression for the normal force Fn exerted on the system. So Fn appears in which diagram? It appears in this diagram, so we'll consider the system. So let's consider the system block 1, 2. Along the vertical, why we're considering the vertical? Because the normal push lives in the vertical dimension. Then no need to apply Newton's second law, we can simply say that Fn would be equal to Fg plus F sine phi. So here we can do the following interpretation. For example, we know that in most of the cases the normal push is equal to the mass of the system multiplied by gravity, which is given by Fg. This is the case if we don't have any vertical forces. Now if we have vertical forces, that would modify the normal push, and this depends whether the force is a pushing or a pulling force. So this is a pushing or a pressing force that would increase the normal push by F multiplied by the vertical component sine phi. And here also let me mention something very important referring back to part B. Since we gave the expression of F21, we need to double check that this expression is being expressed in terms of m, capital M, F and phi, and indeed it's being expressed in terms of these. Although here we have cosine, but cosine is a function and not a variable or a constant, so we won't expect that they will tell us to express in terms of cosine. This is one. Another thing that is important to mention, it is not necessary that our final answer should be expressed totally in terms of these. For example, they told us here and physical constants as appropriate. One choice would be G, but we can notice that our expression is free of G. Okay, this is pretty fine. It is not necessary that our final answer should be expressed in terms of all of these. So it might include all of them or partly. Now getting back to part C, so along the vertical we have the normal push which is up, it's being balanced by the pull of gravity down and F sine phi. We are interested in the normal push, so the normal push, the pull of gravity would be replaced by the total mass of the system m plus m multiplied by g, F sine phi, and that would be the final answer because it's being expressed in terms of m, F phi and physical constants as appropriate. Now in part D, we need to calculate A if small m is given by 300 grams, capital M is 560 grams, F is 12 newtons, and phi is 30 degrees. Then here, you need to make sure that your calculator is set up in degrees. These masses should be converted to kilograms. Now the acceleration is given by that, replacing the value, plugging that on the calculator. We have the value of the acceleration to be 12.08 meter per second square. And this is relatively a large acceleration compared, because we know that the acceleration due to gravity is given by 10 meter per second square, which is pretty large acceleration. So what about 12? So it's relatively large. Now in part E, does the acceleration and the normal force Fn of the system increase, decrease, or stay the same if the pushing force F becomes horizontal? Justify your answer. So let me split this part into two parts. So first we need to discuss what happens to the acceleration if the normal force of the system, if the pushing force becomes horizontal. Now let me say that this force is given by 5 newtons. Then for example, for a certain angle of phi that we don't know at this moment, although it was given previously by 30 degrees, but let's ignore this fact. So one decomposition might be that this force F can be decomposed into 4 newtons like that, and 3 newtons down, because we know that according to the Pythagorean sum, radical 3 square plus 4 square would be 5. So this is a perfect example on the decomposition of 5 newtons along the horizontal and along the vertical. What can we say about that? The force F in total is 5 newtons, but only 4 newtons compensate for the horizontal acceleration of the block. Now here what we're saying, if F completely becomes horizontal, so there will no vertical component anymore. So in this case, if this completely becomes horizontal, these 4 newtons would change to 5 newtons. Then the horizontal component of the force increase. In this case, the acceleration increase simply because we have increased the horizontal component. Remember that the acceleration was given by F cosine phi divided by the total mass. Now the maximum acceleration occurs if this is completely horizontal, which means this is 1, phi is 0, which makes the acceleration increase. So regarding the acceleration, we can say increases. So first we need to specify whether increase, decrease, or stays the same. That would compensate for part of the grade. Okay, the other part is to justify the answer. What is the justification in this case? As the horizontal component of the pushing force increases, the acceleration increases from being F cosine phi divided by the total mass to being A given by capital F divided by the total mass. Now what about the normal push? Now the normal push in this case is given by Fg plus F sine phi. This comes from the vertical component. Now if the force F completely becomes horizontal, then phi becomes 0, then this part will disappear. So the normal push will change from being Fg plus F sine phi into Fg, which means the normal push has decreased. Then we can say decreases, this is part of the answer. And we say as the vertical component of the pushing force decreases, the normal push decreases from being Fn, which is m plus mg plus f sine phi, into m plus m multiplied by g. So here, if I want to give you a marking scheme, increases would be credited as a half. This statement would be credited as a 1, let's say, for example. This would be credited as a half, and this would be credited as a 1. So for the correct choice, we have a mark, and for the correct reasoning, we have a mark. Now let's move on to problem 2. In problem 2, what do we have? 3 blocks X, Y, and Z of masses M1, M2, and M3 respectively are pulled via a constant horizontal force F and thus accelerated by A. The system that we have is being accelerated by a force F, and it seems that they're gonna move to the right. Then let me choose the right direction to be the positive. They are connected to each other by chords. X and Y are connected by chord 1, and Y and Z are connected by chord 2. The chords are massless and inextensible. Now the meaning of massless and extensible, that the tension here along chord 1 is perfectly the same. So this is the tension T1, and the tension here along chord 2 is perfectly the same to be tension T2, and these two statements will be referred later in the next or upcoming video. And remember that express all algebraic answers in terms of M1, M2, M3, F and physical constants as appropriate. Then now whenever we have or we need to derive an expression, we need to make sure that our expression is being expressed in terms of these. Not totally, it might be partly. And in part A, we would be expected to be asked about the FBDs in order to utilize later Newton's second law. And here we can consider different configurations: X alone, Y alone, Z alone, or the system combined. For the block X, we have the pull of gravity down, the normal push up, and the tension T1 to the right along the chord 1. Now for block Y would be the pull of gravity down, the normal push up, the tension T1 to the left, and the tension T2 to the right. Now notice that here carefully T1 and T1 are represented by the same magnitude but with opposite direction, because for X communicates with the chord with the tension dragging it toward the right, whereas Y would communicate with the chord 1 with the tension T1 pulling it toward the left, because always the tension acts away from the object, whereas the tension T2 would be away from the object to the right. And notice that I have represented T2 to be greater than T1, which reflects the fact that block Y would accelerate toward the right. Now for block Z, it will communicate with the pull of gravity, the normal push, with the tension T2 left and the pushing force F to the right. And notice that I have represented T2 and T2 with the same length. As for the system as a whole, we will not care about chord 1 and chord 2 because they are something internal within the system. So we have the pull of gravity down, the normal push up, and the pushing force to the right. Now in part B, derive an expression for the tension T1 along chord 1. Now T1 appears in the FBDs for block X and block Y. For the same previous argumentation, I will consider block X because it's being acted by the least amount of forces. But before doing so this configuration is pretty the same for boxes on a level surface, and now we're familiar with the fact that before we proceed with the internal forces, we need to determine the acceleration of the system, and this can be done by considering the system as a whole. Now let's apply Newton's second law. We have the pull of gravity, the normal push F, and the total mass of the system multiplied by the acceleration. Along the horizontal, taking the right direction to be the positive, we have 0 plus 0 plus F, total mass and the acceleration. Then the acceleration is given by the total force divided by the total mass. And now we can consider Newton's second law for block X. We have the tension T1 plus the pull of gravity plus the normal push is equal to M1A. Along the horizontal again, 0 plus 0 plus T1 is M1A. And now for A, it would be replaced by the expression that we have determined above, and factoring out the fractional mass, we end up with this expression. And now let's do the check. Indeed, it's expressed in terms of M1, M2, M3 and the total force, and they are listed here as well, and no need to include any physical constants at this stage. Now derive an expression for the tension T2 along the chord. Now here we can either consider block Y or block Z. Now we will consider block Z. You can also consider block Y, that's perfectly the same, because in this case both are symmetric and they have 4 forces. Now what are the forces acting on block Z? T2 plus Fn plus Fg plus F is equal to M3A. Notice that here I have included the mass of the block 3 because we are applying the Newton's second law to block Z. And along the horizontal, notice that T2 is acting in the negative direction. For this reason, it's being preceded by minus sign. F is acting in the positive direction, it's proceeded with a plus sign. The mass is m3, A, it's neither projected. And we're searching for T2. Now we can drag this to the right hand side and this to the left hand side. So that would be T2 is F minus m3A. That would be F minus m3. So A would be replaced by the previous expression that we have determined, total force over total mass. Now we can factor out F from both expressions. That would be 1 minus m3 over the total mass. Now here we can do the common denominator thingy. 1 can be written as m1 plus m2 plus m3 divided by m1 plus m2 plus m3, and in the numerator we have minus m3, so that would be this expression. These would cancel and we're left with m1 plus m2 divided by the total mass. Then the tension T2 along the corridor is given by that, and now we can do the following check. It depends on m1, m2, m3 and F, and then that's perfect. Now we need to determine the acceleration if we have the masses and the value of F. Remember that these should be converted to kilograms, and that is done by dividing by 1000. So now we're ready to calculate the acceleration, and it's given by 25 meters per second square, which is relatively large acceleration. And for the final part E, if the total mass of the system increases, that is increasing the mass of each block separately, does the acceleration A increase, decrease, or stay the same? And notice that they're not asking me for any justification, so we'll just choose the correct variation. And in this case they're talking what happens to the A if the total mass increase. Notice that A and the total mass are inversely proportional. If this increase, this would decrease, so I will go with decreases. Then that's it for me in this video, guys. See you soon in a new one.